for both polarizations, and there's filtering that's done. Fortunately, because it flies over water, we have a lot of data about the bandwidth and multipath that we're dealing with. And so the time constants for these filters are set accordingly. I'm going to talk a little bit about the hardware.
There you go.
Okay, so just took a little time, I guess. I missed a slide? Okay, so here we are, the aircraft again. This is the fuselage, this is the structure, the antenna is towards the back to try and stay away from the engines. The legacy antenna had the entire aperture, and it turns out we only need a small piece of it to get the geometry requirement. This is really a design note slide, but I stuck it in here because there's so much stuff we're trying to cover here. We're synchronizing 224 8-bit A-to-Ds, and each A-to-D has 10 software radio receivers attached to it for 2,200 receivers, and they have to be completely synchronized because you're digitally beamforming. There's a demand-assigned data bus. There's a monopulse tracker, and the side lobe target acquisition is mitigated using complete scan processing. The track update rate is dynamic, and it's driven by the error magnitude of the tracker, and it's not fixed. There's an 8-input optimal combiner for each of those 10 channels. There's a multifunction DMOD with a built-in up converter for IF downlink and tape carrier outputs. There's an AM/FM analog and digital outputs from the DMOD that support FSK and SOQPSK for our requirement, but actually supports more. And there's multi-symbol sequence detection. The software is based in the new Linux, Java, and Python XML. That's Greek to me, by the way. But it's very modular and allows it to be ported pretty easily. And just to verify that the system is working well and has been properly transferred from the test range into the aircraft, there's a portable test source which looks a lot like the antenna, and you bring it up to the antenna, and it makes the antenna believe that there's a beam that it can actually find and track and take patterns of. Before I talk about the pictures, King Aerospace chose this approach over the conventional antenna, even though there were a lot of risks. First of all, there's nothing out there that's like it. And when this was awarded, the FPGA that was required to make this work within power constraints and with the density was not even available. I don't know if they knew that exactly, but it was awarded. The FPGA did show up. Also, there's an issue of the specifications for a synthetic beam antenna is very difficult to reconcile with the classic receiver specifications of RA 106, and so there's constant battles there to try and make the two things jive. And it's also difficult to find advisory help because this is a new application, and if we were to get into trouble, there would be really not many people that could help us. So talking about the pictures now, and I'm going very fast once again to try and keep to the time schedule. We have the antenna aperture right here. It's out in the backyard at Malibu Research, and also a piece of it is in Malibu Research's booth. On the left, you see some of the racks under construction. On the right is one of the chassis with the actual IF cables coming in. The digital beamforming wiring is done through ribbon cables that are very short. The local oscillators, which are all coherent to all these, or these are the clocks to the digitizing hardware. The sync cables to synchronize all this stuff within one clock cycle, and more IF cables. And here you see a back view of the antenna. There's the RF combiner, filter, LNBs, LO distribution. So it's been built, it's under test, and some good stuff is happening. Next, I'm going to show you a block diagram. It's once again, a little complicated, but the point is to orient you about where the subsequent view graphs will be. This is the front end, patches, combiners, filters. Total of 224 outputs that are being filtered and sent to LNBs, which down convert to IF. There's an LO distribution network that synchronizes all the LNBs together, go through a bunch of cables that are not phase matched over to the digitizing equipment, then into the combining equipment, and then to the DMOD. Then it gets put out for retransmission or viewing on the aircraft itself through external instrumentation. It's all supported by a VME bus, VME 64, and a host computer coordinates all of this together. There's a power supply, of course, that's sitting in the back. So what you're seeing in the next view graph are pictures of filtering that's happening at these points. This is the RF that's coming out, the filtering that goes on in the LNB that shows up here just before the digital subarray, as we call it, which is the pretty much the digital receiver, and then the filtering inside the digital receiver itself. So when you look, you see that you get excellent rejection coming out of the LNB out to 12 gigahertz. And that is superimposed here. But even that, because our operating band goes from 2.2 to 2.4, which I'm sure you cannot see, the LNB requires further filtering, have a bunch of tight filters that are properly placed, and there's some jockeying done inside the LNB to make sure that the spectrum is inverted, so you get advantages of filtering. So you get a fairly narrow output coming out from the LNB, and then inside that space, there's digital filtering, which has 60 dB rejection. Here's an actual data that was taken from the filter that's been formed inside the processor. Greater than 60 dB rejection, stop band, pass band ratio of 1.85 to 1. The bandwidth range of this filter goes from 10 kilohertz to more than 30 megahertz. Okay, now we're using this diagram again to show the next set of slides, which will be looked at right there, which is the output of the combiner. Okay, this is actually was a surprise to us. These are the MATLAB simulations, and we put this in a range, and we took a pattern, and that's the actual measured data. And initially, of course, we didn't believe it, and our customers didn't either, and I had to actually stand in front and wave a metal lantern in front and watch the side lobes dance before I could even convince myself that this was real. Because, you know, this was developed using simulation, and it's just one software switch to go from simulation to real signals, and it's easy for the computer guys over there to not have flipped that switch. At this point, I'm a believer too. So mutual coupling was, we thought, going to be an issue, but because it's a digital beamformed antenna, the mutual coupling, whatever it is static. And once you calibrate that out, it stays calibrated out. So the issue has then to do with second order effects, such as the ground plane not being exactly right and things like that. So the antenna side lobes were almost ideal. We were very surprised. Okay, so the next slide jumps from there into tracking. So picture this antenna on a pedestal. The source is in the far field. We're moving the antenna to minus 60 degrees, which means the beam is scanning to plus 60 degrees. Then we're moving the antenna to plus 60 degrees, which means the beam is scanning to minus 60 degrees. And then we're returning the antenna back to the center. So that's what you see over here with the blue line is the set of measurements, but also there's a